it's good to check your work. You should take that original matrix A and multiply it with this and see if you get the inverse. I'm not going to do that on the board. I invite you to try that yourself just for extra practice. But you can always check your work just by multiplying these together. So anyway, just in summary, give you a square matrix, make the augmented matrix with A on the left and identity on the right, and then try to reduce the left side so that it looks like the identity. If you can, then this right side is your inverse. Okay, cool. Now, let me talk a little bit about when there is not an inverse. How would you know if there's not an inverse? And what I should say is the algorithm will basically tell us this as well. So we can use this algorithm to determine if there's not an inverse. Okay, so let me erase this and tell you when there's not an inverse. So when is there no inverse? Or when is there not an inverse? And it's very simple. Basically, A has no inverse. In this class, we'll say A has no inverse when it's not possible to reduce this augmented matrix AI so that the left side is I. So basically, we're saying if it's impossible to get I on this left side by doing that reduction that we just did in that last example, if that's just not possible, then there's no inverse. And how would you know if it's not possible? This happens when it's reduced. Is reduced, but is not I. And I'll put some examples on the board in a second. So you guys should remember from chapter 5, when we solved systems of equations with a matrix, there were 3 possibilities, right? There was either exactly one solution, in which case then your reduced matrix would look like I. We'd get 1s down the diagonal and 0s everywhere else. That meant that there was one solution only. The other possibilities are that there were no solutions or there were infinitely many. And in those cases, our matrix didn't look like I. For example, I would have maybe rows that are missing leading 1s or something, right? Or I'd have arbitrary parameters. So I'd have columns that are missing leading 1s. So I'd have somewhere in my matrix, I'm missing a leading 1. And it turns out if my matrix, when I do this, looks like one of those situations, then there's no inverse. There's no inverse. So I'll throw a couple examples on the board just to make it really clear. Some certain situations where there's no inverse. So for example, say you're reducing your matrix, and I have a bunch of stuff on the right, but on the left, my matrix ends up looking like this, maybe. So notice here I have a row of all 0s. So that means it's impossible to get a 1 here, just to get a single 1 here. There's no way I'm going to get it here. And so, I mean, no matter what these were, there's no way I'm going to get like a leading 1 right here. And so this would have no inverse. It has no inverse. Because we think back to chapter 5 context, this looks like a matrix that maybe would have infinitely many solutions, or a system with infinitely many solutions. So since this is reduced, but it's not the identity matrix, there's no inverse. Here's another example. Again, there's some stuff in the right, whatever. Say we've reduced our matrix, and it looks like this. Yeah, basically it's going to be kind of like that one. Again, we notice in this column I have an arbitrary parameter. That's maybe what I should have said about this one. I have an arbitrary parameter. So it's reduced. So I have one arbitrary parameter. This thing's reduced. That means that there is no inverse again, because there's no way to make this look like I. So again, there's no inverse. Okay. So when determining if the matrix has an inverse, our algorithm just tells us to reduce the left side. And if when it's fully reduced, it looks like I, then there's an inverse. And if it doesn't look like I, if it looks like something like this, then there's no inverse at all. And so you can just say there's no inverse. As far as we're concerned in this class, there's no better way, except for one special case, which you'll see on an activity. Maybe you've already looked at that. For 2x2 matrices, there's sort of another way to see if it's inverse, see if a matrix has an inverse right away without doing this algorithm called the determinant, which we're not going to explore much further in this class. Again, you guys will see it for 2x2s on the activity, but that'll only apply to 2x2 matrices. So if they're 3x3 or bigger, you have to just do the algorithm, unfortunately. There's no other way to just sort of look at it and decide if it's invertible or not. Strictly speaking, that's not true, but in this class it is. So in this class, if you have a 3x3 or bigger, you just have to do the algorithm to determine whether or not there's an inverse. So we'll leave it at that. The algorithm, I'm having trouble saying that word. The algorithm will always work. It'll either tell you there is an inverse or that there's not. So, okay. Let's see. Okay, so to sort of finish this section off, I want to just tie back to this discussion of division, because I've told you what an inverse is, and I just want to sort of reinforce the fact that this is really going to allow us to sort of divide by a matrix. Keep doing air quotes because it's not really the same. I don't know. I don't want to call it division. No one else calls it division, I suppose, in matrix context. But I just want to tie it back in so that I see, why did we just spend this time finding this inverse? So let's do dividing by a matrix. And really quick, let me just remind you again, when it came to numbers, I told you guys that basically multiplication and division are sort of the same thing. Because if I want to divide by 2, or any non-zero number, this is really the same thing as multiplying by 1/2, or its reciprocal, if you will, right? And I told you that the reciprocal of a number is really its inverse. There's another word I could use for it. So this is the analog to a matrix inverse, is the reciprocal. So when I divide by a matrix, I want to think about, so when I divide by A, I really just want to multiply by A inverse. Yeah, that's what I want to do. I want to multiply by A inverse. These are quotes. Maybe I don't need the quotes. Anyway, so the divide by A, I'm going to multiply by its inverse instead. That's our sort of division operation for matrices, if you will. So we multiply by an inverse. This is slightly trickier now than the number situation, because remember, guys, what I told you. So recall the following fact, and then we'll do an example here. Recall that in general, A times B is not the same thing as B times A. The order of multiplication for matrices matters big time. So B's are not going to be the same in general for matrices, but when it was in just numbers, it didn't. This was, X times Y is the same thing as Y times X if those are numbers. 2 times 3 is 3 times 2. We didn't have this issue with numbers, but we do for matrices. And this could come back and bite you if you don't remember this, and here's why. Let's see an example. We want to solve matrix equations. So let's try to solve AX equals B for X. Everything here is a matrix. And as far as the dimensions and everything, let's just say that they all are sorted out so that everything here makes sense. A times X is defined and it's equal to the matrix B. So everything here makes sense. These are all matrices. So this is matrix multiplication and it's equal to the matrix B. How would I solve this? Well, if we think about numbers, if these were numbers, how would you solve for X? You'd probably divide by A, right? To solve for X. And that's exactly what I want to do here in the matrix context, but I just got to be a little careful about what that means. I just told you that dividing by A means multiplying by A inverse. So I want to do that, but where do I multiply by A inverse? You know, this part of the equation, this AX, has two sides. There's a left side and there's a right side. And by what I just told you, it kind of matters which side you multiply on. Which side you multiply by A inverse on. Since A is on the left side of X, maybe it's reasonable to say that I want to multiply this on the left side by A inverse. And that is exactly what we want to do. We're going to multiply on the left by A inverse. And we have to just make sure that we do that on both sides of the equation. Otherwise, we're changing something and it doesn't make sense anymore. So on both sides of the equation, we're going to multiply to the left by A inverse. And we just have to be really careful because, again, we have this problem. So it matters which side you multiply on. When we did number equations, it didn't matter. But now it does. So let's do this. So I'm going to take A inverse times A times X equals, so it's A inverse on the left. And now I have B over here, and I'm going to have to multiply this by A inverse. But again, I have to make sure that I do it on the left. Has to be on the left. If you write this on the right side, you've messed up. This no longer is true. Because probably these are not equal. So make sure it goes on, make sure you're consistent and put it on the same side on both sides of the equation.
I have a quick question.
Yes.
Could you repeat one more time why we have to do it on the left?
Right. So the reason I want to multiply on the left is because A is on the left side of X, and I want to cancel out the A. Right. I want to move the A to the other side.
Okay. Thank you.
Yep. And then since I multiplied this side on the left by A inverse, I have to multiply over here on the left by A inverse also. Okay. So yeah, good question. Now we just use our property of inverses. What's A inverse times A? That's the identity matrix by properties of inverses. I mean, that's what an inverse is. It's the thing that gives me the identity. And then nothing changed over here. And now what's the identity times X? Well, the identity is the thing that doesn't change anything when I multiply by it. So this is just X equals A inverse B. So here's our solution. X is A inverse B. So we've solved our first matrix equation, if you will. Granted, these were just random matrices that we don't know anything about, but here we go. And I'll point out, this only makes sense if A has an inverse, of course. If A inverse exists, then this makes sense and there's no problem. But it might be that A has no inverse, in which case I actually can't solve this then. Then there's, this no longer makes sense. Or at least I can't solve it like this, if that happens. So just be aware. I think usually when we're solving these kinds of things, you will get to assume that they have inverses, or they just will. So you may not have to worry about it too much, but I'll point it out. Okay. So I'll stress again, when we divide, we multiply by the inverse. And you just have to be careful about where you're multiplying by the inverse because order matters. Okay. And on the activity that I posted today, there's a few problems where you're basically going to solve equations kind of like this by doing this. You'll have to be careful about where you multiply by the inverses and such. Okay. As one last thing, maybe, actually, where are we on time? 30 minutes left? Okay, that's good. Let me tell you guys one more thing to tie this all back to chapter 5. Back to chapter 5. So this actually relates back to systems of equations and solving them. And I just want to hammer that home right now, is how to relate this back to systems of equations, because that was our original use for matrices, is writing down the augmented matrix for a system and then reducing it to solve the system. So how did that work? Well, I'm just going to give a really simple system. And maybe I'll just do